Today's a good day to learn about electron configurations. By the end of this video, you should be able to write an electron configuration for any of the atoms on the periodic table. For today's timeline, we're looking at first a recap of shell models, what they are, and some words that we used with those, so valence, ground state, excited state. Then we're going to move on to making the electron configurations, how we're going to write the long version and the abbreviated short version of an electron configuration. And then we're going to use that electron configuration to determine or predict the charge that an atom will have. Let's waddle right in to this lesson. So our recap here. The valence shell, if you recall from the shell model lesson, if you haven't seen that, please click on the link in the description below or on the info card up there in the corner. As a quick review, the valence shell is the outermost shell. So when you're drawing a Bohr model or a shell model, it's the shell that's the farthest away from the nucleus. This is also the highest energy shell. In that shell, we have what's called valence electrons. So the electrons that are living in that outermost high energy shell are called valence electrons. These electrons have really high potential energy. And in fact, these electrons have the highest energy for any of the electrons in that atom. Here's a few new words that we hadn't known from the shell model, but that I would like you to know before we jump into this lesson. The ground state, or as I like to say, the ground state, is where you're grounded. Those are all the electrons in their homes, in their shells, where they belong from the beginning. So the ground state is if you were to fill in the shell model or the Bohr model from the lowest to the highest energy level, so from inside working your way out on those rings, on those shells, and as long as you just stopped putting on shells and electrons, once you ran out of electrons, that's the ground state. But in reality, atoms have empty shells that are farther out, farther distances out than what you portray on a shell model once it's completed. When an atom gets excited, so if you add energy to it, if you zap it, if you add electricity to it, anything like that that can excite those atoms, we get into the excited state. That's what I like to call it. So all of the electrons are in the excited state. If you add energy to them, they can jump up rungs like a ladder. So they can actually climb up into those higher energy shells that are normally empty if they're not energized, and then those electrons can fall back down. This is important to note because electron configurations are only determining an atom in the ground state. So we're not talking about atoms that are in the excited state, we're talking about atoms that are in the ground state. So just your stereotypical shell model, no energy added, just real chillax atom. All right, so before we get started on electron configurations, I'd like you to think for a second about the order in which you get dressed in the morning. Or maybe you don't get dressed in the morning. I don't know. I'm not judging. There are days I hang out in my pajamas for like the majority of the day. But if you are going to get dressed in the morning, what is the typical routine that you do? I'm hoping if you're thinking about this, you're not saying, oh, well, I first put on my pants and then I put on my underwear and then I put on my shirt and then I put on my bra. So like Superman here, he would have been a great example of putting on your pants first and then your underwear. Not typically the socially accepted thing to do in terms of order of getting dressed. And there are also stereotypical social norms, if you will, for the periodic table, for the order in which we would dress atoms, the order in which we do things. So likewise, when we're doing these electron configurations, the order is actually really important, the most important thing here. So please keep in mind, just like it's important not to put your underwear on the outside of your pants, it's the reason why we want to make sure that we do the order correctly for electron configurations. So electron configurations, what are they then? Essentially, they're a way of classifying an element. So other than saying fluorine, I could show you this long list of numbers and letters, and you'd be like, oh, that represents fluorine. It's kind of like computer code. So if you think of code as like the 10001111110, all that kind of like different coding, which doesn't make any sense to us, but to computers, they're like, oh, that means, I don't know, my human is clicking the right button too much. Whatever it might be for a computer language is the same thing for electron configurations. You basically have these numbers and letters that represent an atom and its location on the periodic table and the number of electrons it possesses in the ground state. Again, this is where that comes back. It's not the excited state, it's the ground state. This is just your basic chill atom on the periodic table. Another way to think of electron configurations is that they're sort of like a shortcut to the shell model. So instead of having to draw a whole bunch of shells and do ring around the rosy, buckets full of all the way around the shell, it's just writing a straight line, like a sentence for that atom. And it's actually a lot easier once you get the hang of it. So with just a little bit of practice, I think you'll be confident enough to say that, yeah, these are 100% easier than having to draw a million circles and count dots every single time. The benefit of an electron configuration is that it also tells you what energy the electrons are living in and what orbital they're living in, based off of the shape of an orbital and the level of an orbital. So if you think about the periodic table, again, if you haven't seen my lesson on the periodic table, please click on the link in the description below or on the little card that's popping up in the corner up there in order to familiarize yourself with the periodic table organization as well. This is another way that the periodic table is organized. Those rows that we talked about, those periods going left to right, those levels are now what we're going to refer them as. We're going to say levels as opposed to periods in this case. So there are 7 levels when we're looking at the periodic table. As you can see that there are a max of 7, as you can see there. 7 is the largest number that we see in terms of a level. The groups now, or the families, are also going to indicate something different in this grouping for electron configurations. They're going to represent the orbital shapes, and those shapes are known as S, P, D, and F. So we have different shapes. Those are different shapes of orbitals, which we'll get to in the next lesson. The important thing to note here is that in the orbitals, you can only house a certain number of electrons. In the S shape, you can only fit a maximum of 2 electrons. So anywhere where it's S, you can only fit 2. Likewise here, that would only fit 2 electrons. Any place where you have P, like in the P block, that's all of the orange, and you can fit 6 electrons in the P block, maximum. Just like the shell models, you could fit a max of 2, then 8, and so on and so forth. These all have also specific amounts of electrons you can fit in each orbital, in each house. So the D block next, that's in blue, you can only fit 10 electrons, and the F block, that's in yellow, you can fit a maximum of 14. So those shapes that we're talking about, just as a kind of brief intro here, I do talk about these extensively in the next lesson if you watch to the end and click on that to also inform yourself on orbital shapes. But here, just kind of as a general idea so you know what they look like, the S orbital, I kind of think of that as like your single tiny little house, like those mini homes. If you think about those ones that they were trying to push, I guess retired individuals and teachers and all that kind of stuff, like, oh, live in this mini home, or, you know, it's literally like there's a bed up top and it's all within like 400 square feet, this super tiny little house. Think of the S orbital as like this tiny little house. As we mentioned before, the S orbital can only fit 2 electrons. So if we're thinking about electrons like people, you wouldn't in your right mind try to shove more than 2 people into a tiny house like that. So if we have this tiny little mini home, we're fitting a max of 2 people, 2 electrons. That's it, folks. We cannot fit more than that. The p orbital, I want you guys to think of kind of like the Family Guy household. that fits comfortably 6 individuals. So 6 electrons can fit in the Family Guy household. For the d orbital, kind of looks like a clover, as you saw there, the 4 lobes. So there's kind of more room to spread out in the d orbital. In the d orbital, I want you to think of that as like your standard 3-car garage, like a nice house, right? And in that house, we can fit 10 individuals comfortably. Last but not least, we have the f orbital, and the f orbital is like your mansion. That thing's huge. It's got tons of space. It's laid out really well, and you can fit 14 people in that mansion. I would assume you can fit more than 14 people in a mansion, but I don't know, maybe each bedroom is like 1,000 square feet. Regardless, we're going to assume that the f orbital is like a mansion, and that mansion can only house 14 people. So the next thing to keep in mind is that these electron configurations that we're going to make using our s, p, d, and f, and the numbers that we've described, the 2, the 6, the 10, and the 14, and levels 1 through 7, we're going to use all those numbers and letters together to make our code for electron configurations. Once you have that, that's what leads to the orbital shapes. So if you look at the image there, right there, then you can see that there are different shapes, almost like those stackable dolls that you see in Christmas time, where there's like that, inside of a, a bigger doll, inside of a bigger doll, and it just keeps getting bigger and bigger, and you've got, this whole stackable set of dolls. It's kind of how orbitals are. If you look right here, you can see that the circles are like never-ending gobstoppers. There's like a circle inside of a circle inside of a circle. Those are all of your S or mini home orbital shapes, and they're just on top of each other. The more levels you have, the more layers of that S shape you have, of that S orbital. Likewise, you can kind of see that the F down here is crazy. There's your mansions down there. So you can tell that there's quite a bit of space for the electrons to kind of branch out and have their own 1,000 square foot bedroom, I suppose. So helium is over here on the periodic table. And if we were to read this organization pattern to get ready for these electron configurations, we can think of it as, okay, we are reading the periodic table from left to right, just like you would read a book. So what we're doing is saying, hey, helium is in level 1. And helium also has an S shape. If you notice over here, it's still pink and it says S in it. So it has an S shape. And it has 2 electrons because I counted 1, 2 over. It's also atomic number 2. If we wanted to try this with carbon, carbon is right here. That's where carbon is. And if we were going to read this from left to right, we would say, okay, we've got 1s, 1s2, 2s, because we have to go through it reading from left to right, just like reading a book. And then we would go, okay, now we're over on this side and we're in the P block. So we would say, oh, okay, that is 1, 2, P, and then I have 2 electrons because I went over 2. 1, 2. 2p, 2. So the way this works is altogether you would have 2 electrons in 1s for carbon. You would have 2 electrons in 2s, that's right here. And you would have 2 electrons in 2p, which is right there. Therefore, if we wanted to write out the electron configuration, just so you can kind of familiarize yourself with what it should look like, it would be 1s2, 2s2, 2p2. So let's go over some brief steps and then jump right into doing these. So we're always going to fill lowest to highest. Just like I mentioned before, when you get dressed in the morning, unlike Superman, unless you are Superman, you're going to put your underwear on before you put your pants on. So there's a certain order in which we need to fill these electron configurations, always reading from left to right, top to bottom, till you get to the atom that you're looking for or that you're trying to write. for an electron configuration. So always think about starting with the lowest level first, and that lowest level is always going to be 1, working your way up to 7. The orbitals also have a level standard, so you're going to be working your way from S to F. Also depends on where it is on the periodic table. You might not even use the F unless you're looking at the intertransition metals. Here are some steps if you'd like to pause the video and write them down for your notes for future reference. Step 1 is to locate the element or the atom that you're trying to write the electron configuration for on the periodic table. That means you're going to need your periodic table available to you so that you can actually locate its position here in order to write the electron configuration. If you don't have a periodic table out, you can't write the electron configuration. You need this present in order to do that. Unless you've memorized this in your head, then kudos to you. So always start with 1s. 1s is hydrogen up here. 1s1 more specifically would represent hydrogen because hydrogen has 1 electron. But for any of these electron configurations, if we're writing the long way, we will always start with 1s. You're going to then fill in the levels of the orbitals as you go until you get to the atom's position. So if you're looking for gallium, you read from left to right all the way through until you get to gallium. So once you get to gallium, then you stop. That's going to be your electron configuration. And don't skip over levels. So you need to read that just like you would read a book. You wouldn't skip sentences in between unless you were speed reading. So no speed reading in chemistry. Third, you're going to fill in levels for D and F. D is right here, our D block, our transition metals, and F are our inner transition metals. They're kind of weird because they're either a level or 2 levels below the rest of everything else. So if you look at the way I wrote out this periodic table, you can see I have 1, 2, 3, 4, 5, 6, 7. That's pretty straightforward. But when you get to the D block, we're 1 level below. So instead of 4, it's now 3, 4, 5, 6. And if you go to the F block, you'll see that it's even another level down. So this actually starts here where it's inserted. So instead of 6, it's actually 4 and then 5. So the D block is 1 level below, the F block is 2 levels below. Just kind of a weird thing to keep in mind there. Let's go ahead and try this. We're going to write the electron configuration for boron. As a reminder, you're always going to start with the number of the level, the letter, and then the number of electrons. That's basically equivalent to saying you're going to do the level number, the shape of the orbital, and then the number of electrons that are in that orbital. Let's give this one a try. Step 1 is locating boron on the periodic table. I've got my periodic table here, and boron is right there. So boron is right here. What I want to do is start with 1s, as I mentioned before. So I'm going to write 1s. Excellent. Now I need to start reading across the periodic table. So 1s and hydrogen fits 1 electron. So that would be 1s1. Now if I go all the way across, I'm still in level 1, and I'm still in the S block. I'm still in the S block with helium. So now that would be 2. So to read all the way across, it's 1s2. My level is 1. I haven't gone down yet. My shape is S. It's a sphere. It's that mini house. And the number of electrons to get through that first level is 2. Now I can move on to my second level. My second level is right there. So I'm going to write 2. In order to get to boron on this side, I need to go through the S block. There's still 2 atoms in the S block I need to read through first before I can get to boron. So I'm going to write 2 and then S, since lithium and beryllium are in the s block, and they have 2 electrons. 1, 2. Remember, the max that you can fit in S is 2. Now I'm still in level 2, but I've changed my block. Everything over here is the P block. That's all in the P block. So I'm still in level 2, but now instead of an S shape, I have a P shape. So I have the Family Guy house. This is where the Family Guy house is, all of these over here. And for boron, I am 1 into the P. So I'm only 1 right there into the P block. So I would write a 1 as my exponent for number of electrons. This would be the electron configuration for boron, or the long electron configuration for boron. All right, let's try another one. Let's try fluorine. Fluorine. Fluorine is right here on the periodic table. And according to our steps, we're always going to start with 1s. 1s. 1s is hydrogen, and I'm going to count 1, 2. Remember, I have to read all the way across. I didn't change my level. It's still level 1, and I needed 2 to get all the way through that sentence, all the way through the line. So 1s, 2. Now I'm going to move down to my next level, my level 2. So I write a 2. These are all in my S block, so I'm going to write S, and I have to go over 1, 2 to get out of the S block and over to the other side. I'm still in level 2. I haven't gone down yet, so I need to write 2 again. But now I'm in a different shape. I'm in a different orbital shape. Again, remember, everything over here is the P block, the P block. So now we are in the Family Guy household with P, and let's count how many we have to go over until we get to F. 1, 2, 3, 4, 5. Remember that P fits a max of 6. Isn't that convenient that if we went all the way to neon, that would have been 6, and that would have been the last one in P. So it makes sense that for fluorine, it's 5, because that's where fluorine is located on the periodic table. All right, now really, you try it. You should pause the video here and try this one yourself. Locate phosphorus, start with 1s, see if you can write out the electron configuration. All right. Hopefully you paused it and you tried it yourself. If not, we are still moving forward and I'm going to show you how to do it. So phosphorus on the periodic table is represented by a P, and it's right here in the P block. Convenient, isn't it? So we need to write our electron configuration starting with 1s. We're going to count over in level 1, 1, 2. Put a 2 in the number of electrons. Now we need to go down a level to level number 2, and we're going to write a 2. The shape that we are in on this side is S, and I go 1, 2 to fill that in. Since I still haven't gone down yet, I'm still in level 2, so I'm going to write 2. But now I'm in a different shape. I'm in the P shape. So I'm going to write P. And now I need to count how many are in the P there. 1, 2, 3, 4, 5, 6. Convenient that there's exactly 6, and that's the max that can fit in the P block. Now I need to go down to the third level, level number 3. In order to get to phosphorus, circled in green, I need to get through the S block still again. So I'm going to write 3s, 1, 2, and now I can jump over to the other side. I'm still in level 3. I didn't go down, so I'm going to write 3 again, and I'm in shape P. I'm in that P block now again. And now let's count over how many I have to get to P. 1, 2, 3. That is the long electron configuration for phosphorus. Now, if you're kind of bored with the long electron configuration, there's a shortcut. There's an abbreviated version. You just have to locate your atom of interest and then figure out what the noble gas is before it. Whatever the noble gas is before it, before your desired element, you're going to put that in brackets as the first thing, as opposed to starting with 1s. So for the short electron configurations, you are not necessarily starting with 1s anymore. You are starting with a noble gas in brackets. So for example, if we were going to do potassium, instead of writing out potassium, which is K over here, instead of going 1s2 for the first line and then jumping down to the next line, 2s2, and then jumping all the way over and going 2p6, and then going down another level to 3 and going 3s2 and jumping all the way over and going 3p6, and then finally ending up in level 4 where you're finally right there with potassium and saying 4s1. Instead of writing out all that gobbledygook, you can see how it could get monotonous and very long. What we can do is just go back one. So from potassium, let's erase this other stuff first. From potassium, if you go directly across, the noble gas that's directly across from it is krypton. We don't want krypton, we want the noble gas that was directly before it. That would be argon. So think about going back one. So wherever your atom is, pick the noble gas that's behind it. One back, before, above, however you want to say that. It's not the one right next to it, it's the one back a bit. That's where this argon came from in brackets. So AR in brackets basically represents all of that, as opposed to having to write it out. And then you just say, oh, now I'm in level 4, and this is the S block, and I went over 1, 4s1. So a lot faster to do the short abbreviated way. Let's try it for calcium. We still need to locate calcium before we can do anything. Calcium is right here, right next to potassium conveniently. So we need to think about the noble gas that's right before it for the abbreviated. If we go across, krypton is the noble gas next to it, so that is not the one we use. We use the one before it. So we're going to put argon, AR, in brackets, and then we're going to try and figure out what the notation is for calcium. Calcium is in level 4. It's in the S shape or S block. So we're going to write S. And we go over 1, 2 spaces, 2 electrons. That should be your abbreviated form, your abbreviated electron configuration for calcium. Now that we know how to write long and short electron configurations, we can use these notations to determine the number of valence electrons. Now remember from before our review, valence electrons are the ones in the outermost shell, the highest energy electrons. And we want to know how many there are because those are the ones that can react, or they're the ones that undergo reactions, the ones that are farthest away. So those electrons are pretty important to know what valence we have. The number of electrons in the outermost shell is what we refer to as its valence. For example, if we were going to look at fluorine's electron configuration here, you can see that we're looking at the highest level. Now the highest level in this case would be level 2. Any numbers of electrons, our exponents, if you forgot, are going to be associated with level 2. So those are the ones we care about. So as you can see, we have 2 electrons in the S shape and 5 electrons in the P shape for fluorine. 5 plus 2 is 7. So what we say then is that fluorine has a 7 valence, or a valence of 7. It has 7 electrons in the outermost ring. You can see this also from the shell model in that we have 2, 4, 6, 7. 7 electrons in the outermost ring. Why don't you give this one a try? How many valence electrons would be in aluminium? Aluminium. Pause the video, give it a try, see if you can figure it out. All right, if you haven't figured it out, first you need to write the electron configuration. You always need to start with that first. So aluminium, located on the periodic table, over here, it's right there. Once you've located it, you can start writing your electron configuration, which I've saved the step for you. It is right here. And now we need to determine what is aluminium's valence. The valence is, again by definition, the highest energy electrons in the highest level. The biggest level number we have here is 3. So those are the only electrons we care about. We don't care about any of this before it. And we want to add up how many electrons are in the 3 level. We've got 2 and 1. So 2 plus 1 is 3. Therefore, aluminium has a valence of 3 or a 3 valence. When we're using the abbreviated electron configuration, this can look a little scarier just because we're throwing in shapes like the D shape and the F shape. So don't get confused when you see those. We're going by the biggest number. For example, if we're looking at gallium, whose electron configuration is right here, that's the abbreviated electron configuration, and you can see that if we're trying to find the valence, we need to look for the biggest number. Even though there's a 3D in the middle of it, we don't care about the 3D because we have a bigger number here. We have a 4. So we're only going to add up electrons from the 4 level, which is higher than the 3 level. So in that case, we would still have our 2 plus 1 giving us a valence of 3 for gallium. Let's try writing the short and long electron configurations for barium and also determining the valence number. If you're feeling like you get it, I really encourage you to pause the video and give this one a try yourself. Otherwise, we're going to jump right into figuring this one out. First, let's locate barium on the periodic table. Okay, so barium is right here on the periodic table, so quite a ways down. In this case, the short or abbreviated electron configuration would be much easier, but let's run through the long one so that you can see the full thing come together. In order to get to barium, we need to start with 1s. And then we need to read from left to right. 1, 2. Now we need to jump down to level 2. We are in the S shape on this side. 1, 2, S2. I'm still in level 2, but now I'm on the P side. 1, 2, 3, 4, 5, 6. Now I need to jump down another level. That's 3. Again, we're over on the S side. 3S, 1, 2. Jump all the way over. I'm still in level 3. Now I'm on the P side. 1, 2, 3, 4, 5, 6. You can see how this could get really tedious. All right, now we're in level 4. 4, again back at S. 1, 2. Now this is where it gets weird, because remember, now we are in the D block. And remember, the D block is weird because technically we are one level below the level we were in before. So even though we were in 4, now we are in 3D. Now let's count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Convenient because only a max of 10 can fit in D. Great. Now we need to go back into level 4. On the P block on this side, this is still level 4, just like the S side. So now we're back at 4, P on the P side. 1, 2, 3, 4, 5, 6. 4P6. Jumping down to level 5. Now we're at level 5. We need to get through the S block first. 1, 2, S2. We need to get through our D block now. D block is weird because it's one behind, so that's going to be 4D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4D, 10. Now we are in the P block again on this side. And now we are back again in level 5, P. 1, 2, 3, 4, 5, 6. All right, we're almost there. Now we're finally in the correct level for barium. That would be level 6. We are back in the S block, and we count over 1, 2. Whew, to get to barium. Now watch. This would be so much easier if instead we just did the abbreviated version. So the abbreviated version of all this gobbledygook we just did would be finding barium, figuring out what the noble gas is before it. We're going to put that noble gas in brackets, and then we're just going to start our reading frame from XE. So from XE, now we're going to go to level 6, count over 1, 2 in this S block, and that would be our entire electron configuration for barium if it were shorthand. So the first one is long, this one is short, and now we need to figure out what the valence of barium is. What is barium's valence? We need to look for the biggest level, the highest number level. The highest number we have is 6 out of all of this. 6 is the biggest number currently present, and 6 has 2 electrons. Therefore, we would say that barium has a valence of 2. Now that we know how to figure out what the valence is, the number of electrons in the highest energy shell, we can also figure out the charges that an atom will become. We can predict those charges. Remember, there's this thing where all of the atoms want to be like the noble gases. They want to be oh so noble and have 8 electrons in their outermost shell. We call that the Octet Rule because they want to have 8. Think octet, octopus, 8 legs. They want to have 8 electrons in the outermost shell. So if we know what the valence number is, we can figure out how close or far away from the number 8 it is and determine whether or not that atom will prefer losing or gaining more electrons in order to obtain that number. So here are some steps that you can jot down in order to predict atomic charge using electron configurations. The first thing you need to do is actually write out the electron configuration. You could use long or short, it doesn't really matter which. Then you need to determine the valence, just as we've done before. You need to find the highest level, the highest energy level, and add up the electrons in the exponents for a total valence number. Then you need to use the Octet Rule, see how close or far away it is from the number 8, and determine how many electrons it would need to lose or gain in order to get to 8. So the way you would then write the charged atom is by writing the symbol of the atom with the charge in its exponent. My example for you is magnesium. Mg is the symbol, +2 is the charge, or 2 plus, it doesn't matter which way you write it. So you could also write it as Mg +2. Either way is fine. It's indicating that there's a charge there. That's just how you could write it. We're going to go through how to do that. Now, the Octet Rule does not work for the transition metals and the elements just to the right of the transition metals. So just keep that in mind. We can only do that for the atoms that actually do tend to have those charges that we talked about, the predictable charges from the periodic table video. Let's give it a try. So using electron configuration, what charge would bromine make? Well, bromine is right here on the periodic table. We're just going to write the short electron configuration because that's easy. Remember, it's not the one right next to it, it's the one before it. So that would be brackets argon, and then we would just count over from there. Level 4, S2, level 3d10, level 4, 1, 2, 3, 4, 5. So we should have that all together there, just as I said. So we have 4s2, 3d10, 4p5. Now if we want to figure out the charge, first we need to figure out the valence. That's the reason why I have these in pink, because those are the highest level. Highest level is 4, so we don't care about that middle one there. We only want to add our 5 plus 2. So then bromine's valence number is 7. That's how we got that 7. From there, we need to figure out, well, what would bromine rather do? If it needs to get to 8, would it rather gain an electron? So would we rather add an electron? Or would we rather subtract 7 electrons to have it back to 0? Have the shell before it have the 8. It might be easier just to gain 1 electron than lose a whole 7. In this case, gaining means that you are gaining negative charge. Since you're gaining an electron, you are gaining negative 1. You are gaining 1 electron that is negatively charged, so negative 1. In other words, you're going to write the symbol Br for bromine, and the charge would be negative 1. It gained 1 negative electron, therefore it is negative 1 charge. All right, you go ahead and give it a try. Using electron configurations, what charge would oxygen make? Go ahead and pause the video here and give it a try yourself. If you just want to see it done, oxygen is right there. We're going to write the short electron configuration. So I'm going to go over, I'm not using neon, I'm using the noble gas before. So I'm going to put helium in brackets, go over to level 2, S, 1, 2, all the way across. Now I'm in 2 level, P block, 1, 2, 3, 4. Excellent. So my highest energy level is 2, which means I have 4 plus 2 electrons for a total of 6 electrons in the outermost shell, or a valence of 6 for oxygen. And 6 is either 2 away from 8, or subtract 6 to get back to 0 to have the shell before it have a noble gas standard, like helium. It would be easier to gain 2 electrons to get to 8 than to lose 6. So if we are gaining 2 electrons, things that are negatively charged, we are becoming negative 2 charge. And we would write that as, oh, my bad, it's behind my head, sorry. We would write that as oxygen negative 2. That would be the charged version of oxygen. All right, now you should test yourself. You should be able to now at this point write the long and short electron configuration for magnesium. And you should also determine the valence number of magnesium and the charge that magnesium should become based off of that valence number. Check the description for the answer, and if you would, please love on a duck a little and subscribe to my channel. That would be a huge help, and I hope this was helpful to you as well. Have a ducky day.
No ducks, no glory.